Hi everyone! So this presentation is going to be about different methods that can be used to find the resonance stabilization energy in benzene and really just analyzing those methods and their practicality and their effectiveness. So CDDT is a chemical intermediate that can be created by combining benzene and cyclohexane. And what we'll see more in this experiment is that the resonance energy of benzene can actually be determined by analyzing the theoretical isodynamic reaction that involves benzene, cyclohexane, and CDDT. So based on the reaction that we saw on the last slide, it could be assumed that the heat of combustion of CDDT should equal the sum of the heats of combustion of benzene and cyclohexane. However, this is just not seen to be true, and that is because it assumes that benzene has no resonance structures, which just isn't true. So then how can we find the resonance energy of benzene? Well, because it is difficult to measure the heat of formation in its gas phase, we can do it in the liquid phase. And in this experiment, we will be measuring the heat of combustion with a bomb calorimeter. So the values that can be measured from the experiment we're doing is the heat of combustion for both cyclohexane and CDDT. Unfortunately, not the heat of combustion for benzene because it is not safe. So literature values for the heat of combustion for benzene and steps A and C in the Hess's law picture that you can see on the slide will be determined using literature values. And then step F, or the heat of vaporization for CDDT, will be calculated by using experimental data that was given. So let's get into the procedure about how exactly this was done. So first, a gel capsule was taken and filled with the sample of either cyclohexane or CDDT and weighed. Then the sample was placed into a sample basket above the bomb, and the wire is positioned so that it just touches the top of the sample, but not the bottom of the sample basket. Then a bomb cover is placed on, and then afterwards an outer ring is tightly secured on the bomb to assure that no explosions will happen. The bomb is then goes through a venting process by using an oxygen tank to pressurize the bomb to 15 atmospheres, and then this process is repeated 3 times. After that's complete, the bomb is officially pressurized to 30 atmospheres, and the oxygen supply is removed. Once the creation of the bomb is done, an oval bucket is placed into the calorimeter. Then the bomb is placed into the bucket and connected to 2 ignition wire pins. After that, 2 liters of water is poured into the bucket, making sure that no oxygen bubbles are escaping, and the lid is placed on and secured with iron rings. The motor for the stir is then turned on and allowed to run for at least 3 minutes before the detonation. Once that's done, the bomb can be detonated and the computer software is used to collect all the data. So once the experiment is completed, we can look at the results. As you can see, we have the graph for cyclohexane and we have the graph for CDDT, and they look pretty similar. But let's get into what some of the marked values on the graph for cyclohexane mean. So going from left to right, Ti is the time of initial temperature about 1 minute after the stir is turned on. Then Ta is the time that the bomb was detonated. Tb is the time at 60% of the total temperature change between points A and point C, and Tc is the time at the maximum temperature. Then finally, Tf is the time of the final temperature, about 90 seconds after it reached the max temperature. And then you can see that there are R values. So R1 is the slope between Ti and Ta, and R2 is the slope between Tc and Tf. Now, using the values that were on the graph in the last slide, we can plug it into this equation, and this equation calculates the change in temperature over the entire experiment properly. So as you can see, there's a place to plug in each of the values we have, and we can calculate the change in temperature for each of them. So the change in temperature for cyclohexane was said to be 3.9334, and then for CDDT, it's 4.3738, which is greater. Now, once we have the change in temperature that we just calculated, we can put that into the delta U combustion equation. So finding this value allows us to plug it into the second equation you see below, which is to find the heat of combustion. So we can solve for that, and the T2 minus T1, that's just the delta T value, and then we can plug it into the second equation and find the heat of combustion for each of them. So that's how we get our experimental results. So in order to find the heat of vaporization for CDDT, this is when we were given experimental data. We were given a table of temperatures and pressures, and we were also given the equation that you can see on the screen. And as you can see, the heat of vaporization value is in the slope. So by graphing the values out in Excel and making a line of best fit, a linear line of best fit, we can see the slope, and as you can see, it's on the graph there, actually. And then from there, you can solve for the heat of vaporization. So once you have all of the experimental results, you can use Hess's law to solve for the energy resonance of benzene. So as you can see, the first three values on this table here are data from the literature, and then we have the experimental data. And it should be noted that the heat of combustion for CDDT, the sign is reversed when you add it because of the Hess's law. And once you add those all together, you can get the energy resonance of benzene, which in this experiment was calculated to be 1,338.29. The second method that is used in this experiment is SciGress. So SciGress is a computer modeling program, and as you can see here, I've modeled out the structures for benzene, cyclohexane, and CDDT. And from there, you can run an experiment and get the heat of formation for all of those. And once you have that, you just add them all together, and that's how you get the energy resonance of benzene. So definitely a much faster process. And the calculated energy resonance for benzene here is 104.10. So the theoretical resonance energy of benzene is 152 kilojoules. This value is very far off from our experimental value that we got using the bomb calorimetry, which was in the thousands. However, it was closer to the SciGress method. I believe the SciGress method was around 104 kilojoules, so not spot on, but definitely closer. So from doing this experiment, I would come to the conclusion that calorimetry is not the ideal method for finding the resonance energy of benzene. And this is for a few reasons. First of all, the results were not accurate. They were very off. Second of all, it was a very time-consuming process. Each bomb took about 45 minutes to make, and we only made 4, so definitely time-consuming, including the calculations. The calculations also took a long time. And the experiment also just had a lot of room for error, a lot of very large values being multiplied by very small values, and just very particular things that make all the difference. And I'm sure that error was definitely made. So that is why I think that the computer modeling is the best method in this situation. I think it's more accurate, and I definitely think it is more time efficient. It does all the calculations for you. It just gave the heat of formation values, and that you just added them all up together and got it. So I definitely would prefer the computer modeling method, but I think that this was an interesting experiment to do. That's it for my presentation. Thank you so much for listening.